Today we'll look at calculus with parametric equations. We'll look at a few different things to do with those. We'll look at how to sketch out parametric curves. We'll look at how to eliminate a parameter to rewrite a set of parametric equations into a regular Cartesian equation. We'll also look at some calculus. We'll find derivatives for a set of parametric equations and apply that to a few other problems too. So you may have done this before, but in general, when we're talking about parametric equations, we're taking an equation that typically we write in terms of x and y, and we're introducing a third variable, in other words, a parameter, t. So what that means is we'll describe the x and the y, the horizontal and the vertical coordinates, independently of each other, both in terms of a third variable, t. So we'll have a function x of t and a function y of t. And if we were to graph those together, choosing all the possible values of t, that's going to generate or create a parametric curve, which will look in 2 dimensions on a graph like a typical curve that we would sketch with an xy function. However, the main difference is that we'll have a direction of motion as well. So what we can do is we can track sort of as we use increasing values of t in which direction the curve is sort of moving. That's the main difference graphically between the two parametric graphs and the Cartesian graphs that we're used to. Let's take a look at a couple of quick examples before we do any calculus with them. These functions don't look great, right? But we've got an x and y written both as a function of t, and we're writing it as powers of 3. X is 3 to the negative t plus t. Y is 3 to the positive t minus t. And we're setting a restriction on the domain for t. We're restricting our t parameter to be between -2 and 2 inclusive. In order to make a sketch, you could do this just like you've always done in order to plot points, right? With the one exception of now we've got to choose t values instead of choosing x values, and we've got to substitute in those t values both into the x and to the y equations to calculate the coordinate pairs for each. You can see I've done that here, plugging in a handful of values here, -2, -1, 0, 1, and 2 for t. Substituting those t values into each equation, we end up with some symmetry, it looks like, right? For example, when t is -2, plug into the x equation, substitute that in for both t's, we'll get an x value of 7. We'll get a y value of 2 1/9 when we do the same thing. Excuse me, and so on and so forth. You can sort of then go back and plot all of those x, y coordinate pairs, ignoring the t for the moment, and that's going to generate your curve. So we can see how that sort of looks here. I went ahead and connected the dots to look at a sketch of what happens in between. It's important to notice sort of the direction, though, like we mentioned before. If we choose that first point when t is -2, we'll end up with the coordinate 7, 2 1/9, which corresponds to the right side of this graph. That's when x is 7 and y is 2 1/9. And notice as t increases, as t gets larger, those x values are moving back towards this point 1, 1, which is a cusp in the graph. So our graph is actually heading towards the left there as t increases. And then once we reach that cusp, the y values shoot up, and we can see that the graph continues to go up this direction. So we can draw little arrows on the graph like so, and to indicate the direction of the curve. One more example, dealing with some trigonometric functions here. We're not necessarily trying to graph this one, although it is an interesting graph. You'll see a lot more like that one. But what we can do, another way we can sort of evaluate these parametric functions is to eliminate a parameter, to rewrite the function back in terms of solely x and y, sort of like we're used to. That has a small disadvantage of getting rid of the direction of the curve, but it will give us the same exact shape. Normally that's just a matter of substitution, solving for t, plugging it into the other equation to eliminate t. But with these trig functions, it gets a little tricky. Because if you were to isolate t in one of these equations, you'll have an inverse trig function, which we know runs into domain issues when we try to compose those with trig functions themselves. So a neat way to do this is to use the Pythagorean identities in order to rewrite this thing in terms of x squared and y squared. So instead of solving for t, we would take the x equation and square both sides in order to get cosine squared t. And then we would take the y equation and do the same thing, but first dividing both sides by 4. So isolate the sine function first, divide both sides by 4, and then square both sides to end up with y squared over 16. This is helpful because then we can substitute both of those two things into the Pythagorean identity. Cosine squared t plus sine squared t equals 1. And when we do that, we'll end up with exactly what we're looking for. We'll end up with an equation with x's and y's, but no more t's. So replace that first term with x squared, replace the second term with y squared over 16, still equal to 1 on the right side. That has now eliminated the parameter t, and we're left with just a Cartesian equation. This might look familiar, right? This is actually the graph of a conic section, the one known as an ellipse, right? We notice that this looks sort of like a circle except stretched because our denominators of x and y are different here. And you can review how to graph those sorts of shapes as well. There's actually one more. Let's take a look at how to eliminate, as we mentioned, without trigonometric functions, and I think that's a little bit easier. In general, we mentioned that we could just isolate t. That's one way to do it, but it's a little bit faster in this particular example. If we were to not necessarily isolate t, but isolate a common function of t in both equations, in this case something like e of t. If we solve for e of t in the x equation, we'd end up with, e to the power t, right? E to the t power is equal to, just adding 1 to both sides, x plus 1. Rewriting the y equation in terms of e to the t, we can break out that exponent and write that as e to the t squared. And now we can do a substitution without even having to solve for t itself. So simply substituting x plus 1 in for e to the t into the y function, we'd end up with the simple quadratic function y equals x plus 1 squared. And again, we can make a sketch and take a look at the graph there. Notice there is only the right side of that graph being included, and you can think about why that might be the case. We'll do a little bit of calculus with parametric equations too, though. We can, in this section, we'll focus on the first derivative. We can calculate that derivative dy dx, the one that we're used to thinking about, the vertical change by the horizontal change. We use it to describe the slope. We can do that from a set of parametric equations without even needing a Cartesian equation, and that's pretty useful. And it involves the chain rule, right? So if we define x and y both in terms of t, here we call it x f of t and y g of t, then what we can do is we can calculate dy dx by using a chain rule derivative. We can say the derivative of y with respect to t divided by the derivative of x with respect to t is equivalent to dy dx. And we can calculate those two things using the given functions. dy dt is just the derivative of the y function. dx dt is just the derivative of the x function. So here we wrote g prime of t divided by f prime of t. And again, the assumption is that the first derivative of your x function is not 0, because we can't divide by 0 here. So let's take a look at an example of that. In fact, 2 small examples of that. For each of those parametric equations, see if you can determine dy dx. Again, for the first one, we'll calculate dx dt. The derivative of this x function with respect to t is simply 2. The derivative of the y function with respect to t is a little bit more complicated. We'll need a chain rule there. We'll multiply 5 by 1/2 times 2t minus 3 to the power negative 1/2. That's using the power rule, but then the chain rule includes an extra factor of 2 at the end. Rewriting that, simplifying it down, the 2 and the 1/2 will divide out. So end up with 5 over the square root of 2t minus 3. Now, to finish up the problem, to calculate specifically dy dx, we need to divide those two derivatives. We need to divide dy dt by dx dt. So in other words, divide dy dt by 2 in this case. For part B, we've got more trig functions, but it's still doable the same way. Right? Dx dt is 4 times cosine t. dy dt using another trig derivative is going to be negative 16 sine t. And then divide the two in order to get dy dx. Right? So we'd end up with negative 16 sine t divided by 4 cosine t, which simplifies pretty nicely to negative 4 tangent t. And remember, this dy dx is the derivative that we're used to thinking about as the slope of a function. So again, even if we don't have a Cartesian function for x or y as a function of x, we can still address its slope in terms of dy dx, written as a function of the parameter t, which is sometimes a useful thing to do. Another example we can investigate, this one is not specifically just asking for the derivative, but we do need it because they're asking for an equation of a tangent line. And so that we've seen a lot in Calc 1 when we talk about first derivatives and applying them. Here we can do that for these two parametric equations. Notice we do have a specified value for the parameter t. We're fixing t at 2, and we're looking for sort of the instantaneous rate of change at t equals 2. So first do what we did before, find dx dt and find dy dt. We're again just using the power rule for each of those terms. And then divide the two. That's going to give us our dy dx function. We did a little simplifying here, multiply both the top and the bottom by t squared. And it looks like our derivative is, our dy dx is equal to t squared plus 1 over t squared minus 1. So if we need an equation for a tangent line, we're going to have to do some substituting. We're going to need to substitute in t equals 2 into the first derivative to find the slope, but also into the x and y coordinates themselves in order to determine what coordinate pair that line is supposed to cross through. So when t equals 2, we'll do that part first. When t equals 2, your x value would be 5 halves and your y value would be 3 halves. So that means that the coordinate pair at t equals 2 is the point 5 halves comma 3 halves in x, y. Also go in and plug that t equals 2 into the derivative, and we get a slope of 5/3. So we can set up our equation. This is point slope form. Y minus y1, where y1 is your y coordinate. That should be equal to the slope, 5/3, times x minus x1, which is 5 halves. And if you want, you can go ahead and rewrite that. You can simplify into sort of slope-intercept form. It's your choice. Right? Distribute the 5/3 and then add 3 halves over to the other side. We'd end up with 5/3 x minus 16/6, or again, you could reduce that fraction as well if you want to. Let's take a look at another one, dealing with, again, another set of trig functions. A slightly different question. Determine all the points that have this particular slope of 1/2 for this parametric curve. We can approach this kind of the same way. Right? Since we're given a slope to look for, we can calculate dy dx and set that equal to 1/2 to determine which t values would cause a slope of 1/2. So that's our plan. We'll find dx dt, we'll find dy dt, similar to what we did before. We'll divide those two things to get dy dx. It looks like that simplifies to negative cotangent of t for this example. And so then what we need to do is we need to set that negative cotangent t equal to 1/2 in order to find all the t values where the slope is 1/2. So we've got a trig function, or rather a trig equation to solve. We can do that. We can isolate cotangent t by multiplying both sides by -1, and then take a reciprocal to rewrite in terms of tangent t instead. You don't technically have to do that, but I find it easier to do inverse tangent functions than inverse cotangent functions. So that's sort of why I rewrite this way. So in order to isolate t, as we mentioned, we'll use an inverse tangent function. We'll take the inverse tangent of both sides, and that's going to leave us with inverse tangent of -2. You'll need to use a little bit of trigonometry here. You can set up a right triangle and label out those sides that are set forth by tangent of an inverse tangent of -2. But then when we do that, essentially we're substituting in this inverse tangent function into both the x and the y in order to look for those coordinate pairs. So using a right triangle, we can find those exact values. We're going to include a right triangle where we have a tangent value of -2. So assuming we pick our theta angle to be at this particular acute angle. Remember, tangent represents the opposite divided by the adjacent side, so we could label something like -2/1. Using the Pythagorean theorem, we get the square root of 5 for the length of that hypotenuse. So that's sort of where this part comes from, right? If we're looking at the cosine of that particular angle for the x-coordinates, the cosine involves the adjacent divided by the hypotenuse, so 1 over the square root of 5. We use a plus or minus there to include both possible signs, and then we multiply by the coefficient of 4. You could do a similar thing for the sine function for the y-coordinates. The difference is when one is positive, the other will be negative, so I wrote a minus plus symbol there instead. All that means is that when x is a positive coordinate, like 4 over the square root of 5, the y one will need to be negative, -8 over the square root of 5. And then the opposite signs would apply as well. One last example that we'll take a look at has to do with calculating the area underneath a parametric curve. So remember, typically we found the area under a curve by finding simply the integral of a function from one point to another, and that's represented here. If we replace that integral of f of x with the integral of y dx instead, you can see sort of how we might be able to use parametric curves here instead. Right? We can write y as a function of t. That's kind of represented here as a g of t. But the question is, how would we rewrite dx as a function of t? And we can do it, but we're going to need to find the derivative of that x function. So we'll calculate dx dt, sort of like we were doing earlier, but then multiply both sides by dt to isolate dx. And what that lets us do is we can do a substitution then. We can plug that into our integral formula to generate a formula for the area under a parametric curve. So here we're integrating the range, the limits of integration change because we're using a t variable instead of an x, but we're integrating our y function, that's g of t, but then multiplied by the derivative of the x function. That's your f prime of t dt. We'll try one example of that. There's a sketch of the curve here, but consider this parametric curve, x equals t cubed plus 1 and y equals 2t minus t squared. We can determine the area enclosed, they say, by the x-axis in the curve, so this shaded area in here, right? We're looking for the area under this piece of the curve. And we can do it, right? We know the area is the g function or the y function of t times the derivative of the f function, or the x function of t. And so in order to do it, first we need to determine our bounds, that alpha and beta as indicated in the formula. So we know that the lower bound is going to occur at this place when y equals 0. And the upper bound is also going to occur at another place when y equals 0. So here we let y become 0. We set the y parametric equation equal to 0. That gives, once we factor out a t, that gives two factors. So we can see that there are two zeros there, when t equals 0 and also when t equals 2. Therefore, 0 and 2 are the bounds of our integral. We know our g of t function that was given to us. We can calculate the f prime of t function. That's the other piece that we'll need. The derivative of the f of t function, the x function, is just simply 3t squared. So our integral becomes the integral from 0 to 2 of g of t, which is 2t minus t squared, times f prime of t, which is 3t squared dt. This one is now an integral simply in terms of t. You can attack this however you want to. I would go ahead and distribute 3t squared and use the power rule twice. Right? Integrate each of those terms using the power rule, and then evaluate the definite integral at 0 and 2 and subtract them. You can double check the math here. You'll end up with an area under the curve of what comes out to be 24/5.